Troubleshooting spanning tree. I've got to say, when I first learned Cisco, spanning tree was my toughest topic to get. But once you get it, just like all things you have to work hard for, it's pretty awesome. Here's your flyby. Redundancy in network environments is good. We all know this, because if any path or switch fails in this topology here, we have a backup path that allows us to go an alternate route and reach the resources that we need. But redundancy in layer 2 devices could destroy us, because switches by default will take a broadcast message and send it everywhere. That's just what they do. So it will go out these ports, and essentially this one receives it and sends it out this port, and this one receives it and it goes out this port, and you end up with this situation where that broadcast loops around infinitely. Now, some people will point to the time to live as the saving grace, but the time to live is a layer 3 field, as in the only thing that decrements that is a router, and there's no routers in this picture, so you have immortal packets that are going around your network destroying it. And the more of these broadcasts that happen, the worse and worse the problem gets, to the point where the network eventually collapses and everything goes inaccessible. In our little 3-switch triangle, it's easy to spot a problem like a spanning tree loop. But when you take a spanning tree environment into a topology that looks like this, which is actually a very good, clean topology, unlike 90% of the network environments in the world, you can see there's the potential for loops all over the place, because we have redundancy built all across this network architecture, which is a Cisco best practice design. So if we have this, understanding spanning tree and how to figure out which links are blocked and which ones should be active is critical. Well, therein lies the entire purpose of spanning tree protocol. It's to look at your network topology and block the redundant connections, thus stopping the broadcast storm in your network. However, monitoring the currently active connections, so if anything does happen, it can unblock the redundant connections and still keep the network continuity flowing okay, right? So essentially it does that by electing a root bridge in the network, the core of the system, and all the other switches in the network find the best way to reach the root bridge. I'm going to talk about that best way in just a moment. Once all the switches agree, these are all our best paths. They actually call those the root ports, the ones that help them reach the root bridge. Then they go in and block. You didn't think that was coming, right? Animation at its best, right? They block by dropping a tree on all the other links in the network, thus stopping the broadcast storms from happening, unless something terrible happens to that primary. Then spanning tree detects it by sending those BPDUs, that's bridge protocol data units. It's like the sonar of spanning tree protocol, and it goes, oh, primary link's down, whoop. Let's move the tree off of there, and now we have restored continuity. So how does spanning tree do its thing? Well, the first thing that happens anytime you run spanning tree is it elects the root bridge. It figures that out based on the switch that has the lowest bridge ID. Now, what is that? It is a combination of the bridge priority and the bridge MAC address. Now, every single switch, when you pull it out of the box, has the bridge priority of 32,768. So essentially, they all tie by default. So then it relies on the MAC address, which is unique per switch, to break that tie. And the lowest bridge ID ends up taking the cake. Now, what that means is the oldest switch, if you leave it all at default, the oldest switch on your network becomes the root bridge, and everybody points to it at the core. Now, you might say, well, I wonder why they designed it that way. Stability. If they made it the highest bridge ID, then essentially the newest switch would win, and every single time you bought a new switch and plugged it into the network, you would have a complete network reconvergence for spanning trees, because they'd all be pointing to this brand new switch that just joined. So the root bridge is elected, and I'll go ahead and allow this one in the middle to be the root. Now, all the other switches in the network find the best way to the root. How does it do that? Well, it relies on the cost as the primary tiebreaker. Just like you would expect, bandwidth is king in the switch world. So let's just say all of these are gigabit per second links. They all get a cost of 4. Now the switches are watching the BPDUs go around, right? They know the path of the network because these BPDUs are like sonar. They're multicast traffic that floods through the whole network. So switch 2 down here that receives the BPDU receives it this direction and this direction. Does some quick math and it's like, okay, if I go that way, the cost ends up being 8. This way, the cost ends up being, well, not 8, 4. And so it finds the best way to the root bridge, and this becomes the root port. Same thing down here with switch 3. So in this simple topology, which is usually used to teach spanning tree, it's a simple scenario to figure out what is the best way to get to the root bridge. And then step 3 is block whatever's left over. So you can see between these two, the link ends up getting blocked. Now notice where I put the X. The X is next to switch 3 because I'm assuming switch 3 has the highest MAC address of all of them just because I called it switch 3. So it's the last one. So it's got the highest MAC address of all of them. Only one side blocks the link in spanning tree protocol. So switch 2 is going to look at switch 3 and say, okay, you block your side. I'm going to remain forwarding, known as a designated port. So a port that's forwarding is called a designated port. This is considered a block port, which disables the whole link. Now, what if the topology didn't look like this? What if it looked like this? You got the little diamond of switches going on. The root bridge is sitting up top. All of these are gigabit per second links. Now, which one does switch 4 down here figure out is the root path? Well, the cost is the same, so it's going to rely on the lowest bridge ID as the next tiebreaker. What does that mean? That means in switch 4's neighbor chain, whichever one of these switches, let's just say it's switch 2, has the lower bridge ID, ends up breaking the tie. So he's going to say, this is my root port. This one ends up becoming the block port in this scenario because we'll just say switch 3 had a slightly higher bridge ID than switch number 2. So that ends up becoming the active path. The last tiebreaker is the port number, and that works well in scenarios like this, where you've got the root bridge sitting up top, 2 connections down here to switch number 2. It's going to look and say, okay, well, I've got gigabit Ethernet 1/2 here and gigabit Ethernet 1/1 here. It's going to end up preferring the lower port number. This becomes the root port. The other one ends up blocked. Well, let me throw a little zinger at you that sometimes, I don't know why they would do this, but you never know, could end up on a Cisco exam. If you take a switch just like I drew down below and crisscross it, so we've got the root bridge sitting up here, right? And I go like that, chunk, chunk. So port 1 connects to port 2 here, and port 2 down here connects to port 1. Now, which one is the active? Now, I know you're thinking, well, it's the same one, right? The lowest. No, it's the lowest port number on the root. Tricky, eh? So this one ends up becoming the active port. This one ends up becoming blocked because it is the higher port number on the root bridge. So now on to troubleshooting spanning tree. Where can things go wrong? Well, if there is a loop, you will end up seeing a lot of MAC address flapping and a complete broadcast storm. The broadcast storm takes your network to its knees because essentially you've got that broadcast cycling around these switches thousands and thousands of times every single second. But it also starts causing MAC address flapping, where let's just say this guy sends an ARP message. That's a broadcast. It goes out here, and how switches learn MAC addresses is they look at the source address that is coming in. So they see the source coming in this port, and then all of a sudden it comes, well, actually, that goes out that port, comes in this port. port, then it comes around here and comes back in this port again, and then comes around and comes out here, and so you end up with the MAC address table where it's shuffling MAC addresses between ports, back and forth, back and forth, back and forth, again, thousands of times a second. Cisco will detect that and actually give you a syslog message saying MAC address flap. I saw a MAC address over here, then it went over there, It kind of tells you where things are going down in an attempt to help troubleshoot the cause of this. But some switches get so crazy with the MAC address switching or MAC address flapping, I've seen them just crash. I mean, where they literally hit peak, MAC address is flying around, it's like, bah, group, and it freezes and reboots. And actually, that has caused good things in situations that I've been where all of a sudden you've got this crazy storm, the whole network suddenly goes boom and goes back to normal, and you're like, oh, I think it's fixed. And then about 5 minutes later, everything starts going crazy again. What that tells you is, okay, somewhere in the network, there's a switch that's crashing. It's stopping the loop. So let's find out, because you can just sit in the server room, watch the switches. The one that goes amber and then goes dark, that's the guy. So from there, you're able to start trying to detect and troubleshoot where that loop is. Now, I know some of you are listening to this conversation. You're like, Jeremy? Isn't that what spanning tree is supposed to prevent? So, I mean, if you're running spanning tree, why are you having a broadcast storm or MAC address flapping? Good question. That's where the rest of this comes in. First off, you can have temporary spanning tree loops if you have port fast enabled everywhere. Now, port fast is the feature that, boom, switches your switch ports over to active immediately when you plug a cable in. Otherwise, it sits there for a little while. Now, Cisco's best practice in most vendors is now to enable fast or port fast on just about every port except those connecting to switch uplinks, because our devices have gotten faster and faster and faster, and most of the time, especially IP phones, outboot the spanning tree timer. So you have IP phones that can't get IP addresses because the port hasn't gone active yet. So the reason I say short duration is when you enable all your ports for port fast, which is not the best practice. You're only supposed to do the ones that are non-trunking ports. Essentially, clicking this in makes it go active immediately. And if there's broadcast traffic happening at the time, it causes this temporary little spaz broadcast storm on your network. It's not usually a big deal and usually resolves itself pretty quickly, because port fast, as soon as it sees a BPDU, disables the port fast feature. So it'll be temporary. It usually is less than 2 seconds, but I've seen a lot of times when you have a connection like this and this switch gets rebooted, I've actually watched the ports do this. As it comes up, you see them go green, 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 all of a sudden it goes brrrr, ding, and then you see them kind of go amber with spanning tree. So it causes this little spaz that you just don't want. So again, best practice, don't have port fast on uplinks going between switches. I've seen actually people put it on there because they think, oh, well, this makes it go active faster when we're having a convergence issue. That's actually not the case. Right below that, and this is the cause of a lot of them, BPDU filter. This little gem filters out BPDU messages. Literally, the switch just ignores them 100%. I don't know why this feature originated, but I would say a couple months ago, for the first time in 15 years of working in Cisco, used it. And it was actually, I think it was, I drew out this scenario a little bit earlier in this, where I said I had a data center, and it wasn't this nugget, it was a nugget where I was talking about VLANs. I said I had a data center where I had redundant connections like this going to, so this is the data center. I don't know why I drew it like a cloud. So data center, and then I had a carrier that was using Metro E connections to connect to all the different sites down there. And all these different sites literally go straight into the data center. They get their internet access from that data center. It was an awesome setup to do. But the problem is this goes straight into the switches, right? So switch, it's layer 2 the whole way through. And so up here, these are switches right here. And the problem is we were talking as we were designing this out. I said, well, on this uplink, we just need to disable spanning tree at each one of these sites because we don't want that interfering with the spanning tree that's going on at the data center, because only in our modern world, right, can you actually have fiber optic connectivity that spans hundreds of miles that bridges layer 2 connections into a data center. So I was saying, well, we don't want these guys to interfere. And the problem is, I mean, the number of sites they had, I think, was about 50 different locations. And we got on the board. We're like, well, yeah, that's good in theory, but what if? I mean, what if, you're not here, Jeremy, down the road, a network engineer who doesn't really know what he's doing, maybe he's not following the template, he plugs in his switch and forgets to disable spanning tree or something like that. Now you've got it interacting with the spanning tree network at the data center. And I go, good point. So what we ended up doing was using BPDU filter on this guy. This is, I draw this out because I'm like, there is a purpose for this feature. We use BPDU filter on there to ignore the spanning tree packets that were coming in from all of these little subsites, so it could not interfere with the data center. So you can see, very unique use. I've never used it outside of that, but that can cause all kinds of loops if you use that feature incorrectly within a network, because literally, I mean, I use this when I demonstrate spanning tree because it's fun to be able to demonstrate what it looks like when a loop happens. That's how easy it is to cause a loop. Just do something like this, enable BPU filter on both of these switches, both connections, bam, you've got a loop, right? Another thing that can cause a loop, no, probably not a loop, but can cause challenges with spanning tree. I'm just going in a big picture challenges, is root guard incorrectly applied. So what root guard, the feature of root guard is to say, I do not want anybody else to become the loop. That was actually, going back to this discussion, one of the things we initially thought about. We thought, oh man, well, we should put root guard, so if one of these little sites down here try to become the root bridge, then and that's about as far as the conversation went, then what we'll do is disable this link because we don't want we don't want this guy to become the root bridge. And we scratched our head and go, yeah, that's not going to work. Because essentially that disables the link for all of these other sites that are coming in there because it sees one of them pretending to be the root bridge. Where you typically will use root guard, and that's the reason I show that to you, is that would be a big troubleshooting. Don't put it up here. Don't put it at your core, your distribution. Now, most of the time people use layer 3 up here, so it's not dealing with spanning tree anyway. But if you do have spanning tree, root guard doesn't belong here, doesn't even belong here. It belongs here on the interfaces facing the end users, because it is assumed by Cisco and by me and by everybody who's has any respect in the industry that these switches are behind a locked door. Right? You don't have them physically out in the open. Now, sometimes I've been in businesses where there is no official IT room. It's a mop closet, yada, yada, yada. But at the same time, there should be some level of security that keeps these secure, thus making them trusted entities. However, we cannot trust what goes outside of that IT room, right? So that's where the root guard comes in. You can run into challenges when the wrong root bridge is elected. And I should mention this, it's not, you don't see it documented that much, but spanning tree protocol actually has a maximum radius of 7. I don't think you'll see this on the exam at all. I I very rarely have even seen it in Cisco documentation. But essentially, let's just say you have your core, your root bridge, right? So root bridge right here. You connect a switch to that and a switch to that. This is the radius I'm talking about, right? So you go 1, 2, 3. So essentially, when you get 7 switches away, spanning tree is not able to accurately detect if there's loops going on, maybe cross-connected cables, something like that, far beyond, and I'm unable to react to it. So, and now you might look at this and go, well, good grief, who would do something like that? Is that, no, it's even one more, right? 7. Who would do something like that? It happens. It just happens in a poorly planned network that doesn't follow a best practice design like this. It's easy to see. Well, oh, that room over there. You mean we have to run a cable all the way? Why don't you just chuck one over the wall and you plug in a switch, and then over here a cubicle gets lit up that they didn't plan on using, and they're like, oh well, we could call the cable. You see the story, right? So that can cause a problem. Wrong root bridge being elected can cause the whole network to fall to its knees in terms of slowness. Like, let's just say this guy becomes the root bridge. And this, by the way, is an exercise that you may have to do, probably not on the troubleshooting exam, but on the switch exam for sure. Identify, okay, what if that guy became the root bridge? Then where are all the active links? But essentially, you're going to end up seeing that all traffic passes through this switch, which means this beautiful gigabit per second, 10 gigabit per second and beyond network that you've designed performs terribly because it's all running through some switch that you forgot about in the closet. So that's another troubleshooting element of spanning tree. Make sure you set the priority on your root bridges. Don't hear me wrong there. When I say root bridges, there can be only one. It's like the old Highlander movie, right? There can only be one root bridge, but they often have a backup root bridge, which is not a technical term because technically there is no backup. It just says I've set the priority one level higher than the root bridge over here, so if this one dies, this one will naturally take over, right? You want to make sure that you control that. Last one is misconfiguration. I have seen this. This is the number one thing that causes these spanning tree loops, where you have ether channel. That's where one side gets hard coded to on, and then over here you have on. And now when I'm talking about ether channel, I'm talking about LACP and PAGP. Right? These are the negotiation protocols of ether channel that negotiate between the two. And if you set it to on, like you hard code it on the side, it's like, okay, I'm not going to use these. I'll just assume this is part of the ether channel and kind of bundle these together. Well, that's all awesome until this one is misconfigured. And you don't have that on. That's just a normal switch port. Then it can't detect spanning tree loops and things like that that's going on there. I've seen that happen. It's not pretty. So that's why using these negotiation protocols eliminates that. If you have a misconfig, this side, if it's set to something like auto and using one of these protocols, then it's going to say, oh, you're not configured. I'm dropping you out of the ether channel. Second thing that can happen is a native VLAN. I actually troubleshot this not too long ago. Somebody purposely, I can't even remember the exact situation, but they actually, on these switches, purposely set the native VLAN different. Like they use native VLAN, we'll just say 50 and 51 here, because they're like, man, on these different sizes, I can't even remember this. There's something where they're like, I just don't want whatever's happening over here to be seen over here, so we're going to kind of just mismatch the whole thing. And that way it doesn't happen. Well, you ended up with broadcasts that actually went from VLAN 50 to 51. And again, I don't remember now how this happened, but it was ugly. And it actually took down an entire site for a long time because we were trying to figure out what is the deal. And we disconnected it because we're like, we know there's a loop somewhere. So that's what took some time to figure out. Setting that native VLAN to the same is key between your devices. That should give you the information that you need to troubleshoot spanning tree protocols successfully. I hope this has been informative for you, and I'd like to thank you for viewing.